Right now, somewhere out past the orbit of Jupiter, a chunk of ice and rock older than the sun itself is quietly slipping back into the darkness it came from. And it is never coming back. Not in 1,000 years, not in 1,000,000. It arrived from outside our solar system entirely, passed through our cosmic neighborhood once, got studied by more telescopes and spacecraft than almost any object in the history of astronomy, and is now leaving for good. And in the final months of that visit, James Webb did something that even the scientists running the observations did not fully expect. It read the chemical fingerprint of a piece of another star system, one that may have stopped existing billions of years before Earth ever formed. And what it found has quietly rewritten what astronomers thought they understood about how comets and the planetary systems that build them actually come together. This is the story of 3I Atlas, and here's the part almost nobody outside specialist circles has really sat with yet. The strangest discoveries about this object did not happen when it was closest to the sun, and they did not happen when the headlines were loudest. They happened afterward, quietly, while the comet was already halfway out the door. Stay with me, because by the end of this, you will understand exactly why scientists are calling this the most chemically important object to ever pass through our solar system, and why some of what it left behind is still being argued about right now. The story starts on July the 1st, 2025, at a modest observatory in Rio Hurtado, Chile, run by a NASA-funded survey program called ATLAS, short for the asteroid Terrestrial Impact Last Alert System. Its entire job, every single clear night, is to scan the sky for anything that might be heading toward Earth. On that night, it caught a faint point of light moving in a way that did not match anything in its catalog. Within days, astronomers around the world had confirmed what its orbit was telling them. This object was not looping around the sun the way every comet and asteroid native to our solar system does. It was moving on a hyperbolic trajectory, an open, unbound path, with an eccentricity that would eventually be calculated at roughly 14, a number so extreme it makes this the most sharply curved, least gravitationally bound path ever measured for any object passing through our solar system. Only something that arrived from interstellar space, moving too fast for the sun's gravity to ever capture it, could produce a number like that. It was named 3I Atlas. The letter I stands for interstellar, and the number 3 means it is only the third object of its kind ever confirmed, after a strange, cigar-shaped visitor called Oumuamua in 2017, and a more ordinary-looking comet called Borisov in 2019. Astronomers went back through older sky survey archives once they knew what to look for, and found faint traces of 3I Atlas in images dating back to May the 7th, 2025, 55 days before its official discovery, meaning it had been sitting quietly in the data the entire time, unnoticed, until someone finally knew exactly where to look. At the moment it was found, it was already moving at roughly 137,000 miles an hour, and it was still well outside the orbit of Jupiter. That speed alone told researchers immediately that this was not a local object. Comets that belong to our solar system get flung around by planetary gravity, but they do not arrive already moving that fast from that far out. Something else, some other star system entirely, had accelerated this thing long before it ever encountered our sun. It is worth understanding just how different this visitor turned out to be compared to the two interstellar objects that came before it, because it puts everything else in this story into context. Oumuamua, spotted in 2017, tumbled through its brightness cycle in a way that suggested an elongated, almost cigar-like shape, showed no visible coma or tail at all, and displayed a faint measurable acceleration that could not be fully explained by gravity alone, a mystery that generated its own share of headlines at the time. Borisov, found in 2019, behaved much more like an ordinary solar system comet, with a conventional dusty tail and chemistry that mostly matched what astronomers already expected to see. 3I Atlas does not fit neatly into either template. It has an obvious active coma like Borisov, but a chemical fingerprint and an age that place it in an entirely different category altogether, one that nobody had a template for at all. If discoveries like this are the kind of thing that keeps you thinking long after you close the tab, this is exactly the sort of story worth staying with, because the deeper this one goes, the stranger it gets, and there's a lot more still coming. The first real discovery beat arrived about 7 weeks after the initial detection, when NASA turned the Hubble Space Telescope toward the incoming object on August the 20th, 2025. Hubble could not see the solid nucleus directly because a fuzzy cloud of gas and dust called a coma surrounded it, the way it does with most active comets warming up as they approach a star. But by carefully modeling that glow, astronomers were able to put boundaries on the size of the icy body underneath. Their initial estimate placed the nucleus somewhere between roughly 440 meters and 6 kilometers across, an enormous range of uncertainty that tells you something important right away. This object was hard to pin down because, unlike anything studied close to home, there was no prior data to compare it against, no history, nothing familiar to anchor the measurement. Then came the second beat, And this is where things started to genuinely surprise the researchers involved. As 3I Atlas moved closer to the Sun and began warming up, both the James Webb Space Telescope and NASA's newer SPHEREx mission got a look at exactly what gases were pouring off it. In an ordinary solar system comet, you would expect water vapor to dominate that outgassing, since water ice is the most common frozen material comets carry. That is not what these instruments found. In observations from August of 2025, the coma of 3I Atlas was overwhelmingly carbon dioxide, accounting for roughly 87% of the total gas being released, with water making up only about 4%, and the remaining 9% mostly carbon monoxide. A carbon dioxide-dominated coma at that distance from the Sun is genuinely unusual. It suggests the object formed somewhere extremely cold, far colder than the region where our own solar system's comets condensed, in a part of a stellar disk where carbon dioxide ice could survive far more easily than water ice ever could. The comet reached its closest approach to the Sun, called perihelion, on October the 29th, 2025, passing at a distance of about 130 million miles, just inside the orbit of Mars, with its speed peaking at roughly 246,000 kilometers an hour, or about 68 kilometers a second at that point. Before that, on October the 3rd, it made a close pass by Mars at a distance of only about 29 million kilometers, close enough that NASA's Perseverance rover, along with multiple Mars orbiters and the European Space Agency's own spacecraft there, managed to capture images of it, marking the closest any spacecraft had ever gotten to an interstellar object. NASA's Parker Solar Probe, already positioned near the Sun for its own mission, observed the comet from October the 18th through November the 5th, using its WHISPER imaging instrument, capturing roughly 10 images a day during that stretch. Even NASA's Europa Clipper spacecraft, en route toward Jupiter's icy moons, and the European Space Agency's JUICE spacecraft, already traveling toward the outer solar system, both turned their own instruments toward the comet as it passed nearby, adding vantage points that had simply never existed for any previous interstellar visitor. For a stretch of that timeline, 3I Atlas actually vanished from view entirely. In late October of 2025, its position lined it up directly behind the Sun as seen from Earth, a configuration astronomers call solar conjunction, making it impossible for any ground-based telescope to observe safely. It re-emerged on the other side of the Sun in early December of 2025, giving observatories around the world a fresh window to catch it again before it kept receding into the outer solar system. That re-emergence is where the story genuinely shifts, because that is when James Webb turned its full attention back toward the comet. Freshly warmed from its closest pass by the Sun, its ancient ice converted into a bright, active coma that was, for the first time, genuinely ideal for detailed spectroscopic study. Using its mid-infrared instrument known as MIRI, Webb observed the comet on two separate occasions after perihelion, once on December the 15th and 16th, when the comet sat about 205 million miles from the Sun, and again on December the 27th, once it had moved out to roughly 236 million miles. What Webb detected during those two sessions became, according to NASA, the very first mid-infrared chemical fingerprint ever collected from an interstellar object, and the results, published in April of 2026 in the Astrophysical Journal Letters, by a team led by researcher Matthew Belyakov, surprised even the people who had been tracking this comet from the very beginning. The most significant finding from that data was a robust, unmistakable detection of methane. The production rate of methane molecules came out to roughly 14% of the water production rate during the first observing session, and climbed to about 27% during the second, a genuinely large amount for a comet's coma to be carrying, especially since methane is what scientists call a hypervolatile ice, meaning it sublimates or turns directly from solid to gas at extremely low temperatures. Finding that much of it still escaping the comet's surface, even after its closest pass by the Sun, told researchers something important about how cold the environment where this object originally formed must have been. Alongside the methane, the post-perihelion data also confirmed the earlier carbon dioxide readings, though the ratio between carbon dioxide and water had shifted somewhat compared to the pre-perihelion measurements, suggesting the comet's outer layers and its deeper, more pristine ice were releasing gas in genuinely different proportions as the Sun's heat worked its way further beneath the surface. According to the European Space Agency's own summary of the findings, both the methane and the carbon dioxide results point toward a formation environment and an underlying chemistry that differ significantly from the vast majority of comets that formed inside our own solar system. If you have found this rundown useful so far, dropping a like genuinely helps content like this reach more people who would actually want to sit with a story this detailed, rather than the louder, less careful version that tends to spread faster online, the kind that skips straight to speculation without ever explaining what the instruments actually measured. The third beat is where the true age of this object finally came into focus, and it took nearly a year of careful follow-up work to get there. Early estimates, based purely on the comet's orbit and the population of stars in the part of the galaxy it appeared to come from, suggested an age somewhere around 7 billion years, already older than our own solar system. But the real confirmation arrived later, and it came from an entirely different measurement technique. A team led by Martin Cordner at NASA's Goddard Space Flight Center used Webb's near-infrared spectrograph, alongside the same mid-infrared data collected in December, to measure the ratio between two forms of carbon in the comet's gas, ordinary carbon-12 and the heavier isotope carbon-13. Almost all of the carbon in our galaxy is produced inside stars considerably more massive than our own sun, and the balance between these two isotopes shifts gradually over cosmic time as successive generations of stars are born, live, and die, slowly enriching the galaxy with new material. What Cordner's team found was a carbon-isotope ratio containing far less carbon-13 than anything ever measured in our own solar system, or even in the young planet-forming disks that astronomers have observed forming around other nearby stars. Working backward through models of how the galaxy's chemistry has changed over billions of years, the team concluded that this object likely accreted its ice somewhere between 10 and 12 billion years ago, during an early, intensely active period of star formation that astronomers refer to as cosmic noon. For context, our own solar system is roughly 6 billion years old, and the universe itself is only about 8 billion years old. That means 3I Atlas may have already been drifting through interstellar space for longer than our sun has existed at all, quietly carrying its ancient chemistry through the space between stars, while entire generations of stars closer to home were still forming, living out their lives and dying. The team published these results in the journal Nature on June the 22nd, 2026, and researchers involved described it, in their own words, as possibly the oldest object ever directly observed passing through our solar system. Alongside that carbon result, Webb's instruments also picked up something else worth sitting with, buried in the water the comet was releasing. A separate team, led by researcher Nicholas Salazar Manzano, found that the ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen inside the comet's water was dramatically higher than anything previously measured in a comet, roughly 30 times higher than what is typically found in solar system comets, and about 40 times higher than the ratio found in Earth's own oceans. That kind of deuterium enrichment only tends to form under extremely cold conditions, colder than roughly minus 243 degrees Celsius, and combined with the carbon isotope data, it paints an unusually consistent picture. This object formed somewhere unusually frigid and unusually long ago, likely in what astronomers call the galactic thick disk, an older, more scattered population of stars sitting apart from the flatter, younger disk our own sun belongs to. There is a fourth beat to this story, and it is the one that actually pulled 3I Atlas out of specialist journals and into mainstream headlines around the world. In October of 2025, a research team using the UV-ES spectrograph on the European Very Large Telescope in Chile detected something in the comet's coma that nobody was expecting, a plume of nickel gas, later corroborated by additional data from the Keck-2 telescope in Hawaii. On its own, nickel vapor is not shocking. It has been detected before in a handful of solar system comets, including Borisov, the previous interstellar visitor. What made this different was what was missing. Every time nickel vapor has been detected venting from a comet before, it comes paired with iron vapor because the two metals are forged together inside dying stars and supernovae, and travel through space bound to each other as what researchers sometimes call cosmic twins. In 3I Atlas, the nickel signal was strong, and the iron signal was nearly absent entirely. Astronomers scrambled to figure out how that could be possible. Comets are generally far too cold for solid metal grains to sublimate directly into gas, so something had to be releasing the nickel through a different chemical pathway altogether, likely a nickel-bearing molecule that breaks apart more easily under sunlight than whatever compound is holding the iron in place. There's a known natural process involving compounds called nickel carbonyls that could, in principle, explain low-temperature nickel release without any accompanying iron, and most astronomers studying 3I Atlas consider it the most likely explanation, alongside other refractory nickel-bearing minerals that may simply behave differently than iron-bearing ones when heated at extreme distances from the sun. Still, it is worth being honest that at the time of these observations, researchers had not fully confirmed which specific compound was actually responsible, and several published papers described the detection using words like extremely puzzling, because nothing in the solar system's comet record looks quite like it. Interestingly, faint traces of that same nickel-dominant pattern, though far less pronounced, were also spotted in Borisov, hinting that this might be a genuine feature of comets that formed outside our solar system, rather than something unique to this one object alone. Harvard theoretical physicist Avi Loeb, who has spent much of his career searching for potential evidence of extraterrestrial technology, pointed out that nickel without iron is otherwise mainly associated on Earth with an industrial refining process, And he raised the possibility, publicly and repeatedly, that this pattern could indicate something artificial rather than natural. He also highlighted a coincidence in the comet's trajectory, noting that its closest approach to Jupiter in March of 2026 brought it to a distance of about 6 million kilometers, remarkably close to Jupiter's own gravitational hill radius of roughly 5 million kilometers, and pointed to a small non-gravitational acceleration in the comet's path, likely caused by an unusual jet structure, as another data point he considered worth flagging. It is important to say clearly that this remains a minority position within the scientific community. The overwhelming majority of astronomers working on 3I Atlas, including the very teams who made these detections, favor natural chemical explanations rooted in the comet's unusual, ancient, and extremely cold formation environment, not a manufactured origin. A team of researchers actually pointed the Allen Telescope Array, a radio observatory built specifically to search for potential signals from extraterrestrial technology, directly at 3I Atlas during its passage through the solar system, systematically scanning across a wide range of radio frequencies for anything resembling an artificial transmitter. This was not a fringe stunt. It was a peer-reviewed techno-signature search conducted using the same rigorous methodology applied to any other candidate target, and the result was a clean, complete non-detection. No artificial radio signal was found coming from the object at any frequency the array was capable of monitoring. It is a small detail that rarely makes the more dramatic headlines, but it matters, because it shows that when a legitimate scientific question got raised, however unlikely the answer, the response was not to speculate from an armchair. It was to actually go check with a real instrument and to report exactly what was and was not found. There is a fifth thread to this story that unfolded quietly, almost separately from everything else, and it involves something scientists genuinely did not expect this early in the comet's approach. In February of 2026, a team from the University of Michigan, using data collected by NASA's Swift Ultraviolet and Optical Telescope back in July and August of 2025, confirmed the very first detection of water coming off an interstellar object, spotted through the faint ultraviolet glow of hydroxyl gas, a byproduct created when sunlight breaks apart water molecules. What genuinely surprised the researchers was not simply that water was present, but how far from the sun it was already escaping. The comet was releasing water at a rate of roughly 40 kilograms every second, while it was still far beyond the distance where most solar system comets typically switch on and begin actively releasing gas at all. That kind of early sustained activity so far from the sun's heat suggests either an unusually large reservoir of near-surface ice or some additional heating mechanism scientists have not fully identified yet, and it remains one of the open threads researchers are still working through even now. One more small piece of evidence suggesting this particular visitor simply does not behave the way solar system comets are supposed to. By the time Hubble managed to separate the glow of the solid nucleus from the surrounding coma, using multiple observations taken across late 2025 and early 2026 after the comet had already passed its closest point to the sun, a far more refined size estimate finally emerged. The effective diameter came out to approximately 6 kilometers, with an uncertainty of around 0. 4 kilometers, narrowing that original enormous range of possibilities considerably, and confirming that this was a genuinely large object by interstellar standards, notably bigger than Borisov, the previous confirmed visitor. Based on that size and its measured brightness, researchers estimate the comet's total mass at somewhere in the neighborhood of 44 billion kilograms, an object substantial enough that early speculation, based on its unusually faint tail, had briefly floated numbers dramatically higher, though the more refined measurements ultimately did not support the most extreme of those early guesses. The comet's closest approach to Earth came on December the 19th, 2025, at a distance of about 270 million kilometers, roughly 8 times the distance between Earth and the Sun, or more than 700 times the distance between Earth and the Moon. NASA and the European Space Agency were both explicit and consistent on this point throughout the entire encounter. 3I, or Atlas, posed no threat of impact at any stage of its journey through our solar system, and it never came remotely close enough for that to be a realistic concern. It's worth pausing on just how large a scientific operation this actually turned out to be, because the sheer number of instruments involved is itself part of the story. Before 3I Atlas, no interstellar object had ever been studied with anything close to this level of coordinated effort. NASA's TESS spacecraft, a satellite normally used to hunt for planets around other stars, was redirected for a special observation run between January the 15th and 22nd of 2026, specifically to study the comet's rotation and activity patterns using its own dedicated data. NASA's SPHEREx mission, only recently operational, turned its infrared instruments toward the comet in December of 2025, adding yet another independent chemical read on the object, during the exact same window Webb was collecting its own data, giving researchers a valuable cross-check between two completely different instruments, observing the same target at nearly the same time. Ground-based observatories joined in as well. The Gemini North Telescope in Hawaii captured a detailed image of the comet on November the 26th, 2025, carefully processed to correct for the streaking star trails caused by tracking such a fast-moving target, giving the public one of the clearest visual looks yet at what this ancient traveler actually looked like, set against the background stars. More than a dozen separate NASA missions, spanning telescopes in Earth orbit, spacecraft en route to entirely different destinations, and ground-based facilities across multiple continents, all turned their attention toward a single icy object. For a period of only a few months, an unprecedented, almost improvised international science campaign built specifically around the fact that this particular visitor was never going to pass this way again. After swinging past Earth's distance, the comet continued outward, passing near Jupiter on March the 16th, 2026. As of right now, in August of 2026, the comet sits in the constellation Gemini as seen from Earth, still technically observable with a sufficiently capable telescope, but fading fast, growing dimmer and more distant with every passing week, drifting outward at roughly 60 kilometers a second, carrying chemistry that was locked into ice before our sun had even finished forming. It will never slow down, never turn around, and never pass this way again. Here is why any of this should actually matter to you, beyond the fact that it makes for a genuinely good story. Every comet native to our own solar system formed from the same disk of material that eventually built the planets, which means studying them mostly tells us about our own local chemistry, our own small corner of the galaxy. 3I Atlas is fundamentally different. It is a physical sample of material that condensed around a completely different star, under different temperatures, at a different point in the galaxy's entire history, and it drifted here across billions of years without ever being disturbed by our sun's heat until this exact encounter. That gives researchers something they have genuinely never had before, a direct chemical comparison point to test whether the process of building icy bodies works the same way everywhere in the galaxy, or whether it varies significantly depending on where and when a particular star system happened to form. That comparison point is one of the biggest reasons the nickel and iron anomaly matters so much to researchers outside the immediate team that discovered it. It is forcing cometary scientists to reconsider long-held assumptions about how metals get locked into, or released from, ice at extreme distances from any star, assumptions that were built almost entirely on a sample size drawn exclusively from solar system comets. This is not a discovery that overturns existing physics. It is a discovery that gives long-standing models their very first genuine external check, sampled directly rather than inferred indirectly from a distance. Naming conventions matter here too, and they are not simply bureaucratic trivia. Under the system the International Astronomical Union uses, the leading letter tells you what kind of object you are looking at, and the number tells you how many of that kind have been formally confirmed so far. The I in 3I Atlas marks it as interstellar, permanently distinguishing it from every comet that was actually born inside our own solar system. And the number 3 tells you, at a glance, that humanity has only 3 confirmed sightings into what is almost certainly an enormous ongoing population of these objects drifting quietly through the galaxy, most of which we have simply never had the technology to notice until the last decade. That technology is about to improve dramatically. Scientists at the newly operational Vera Rubin Observatory in Chile, which carries the largest camera ever built attached to a telescope specifically designed for exactly this kind of wide, fast sky survey, expect to find many more interstellar objects in the coming years, possibly dozens over the next decade alone. Some researchers are already unofficially referring to whichever one turns up next as 4I, whenever and wherever it happens to be found. Unlike the Atlas survey, which was built primarily to hunt for asteroids that might threaten Earth, and only found this comet as an incidental byproduct of that broader search, Rubin's survey strategy is specifically designed to repeatedly scan enormous swaths of sky night after night, dramatically increasing the odds of catching a fast-moving interstellar object early in its approach, while there is still enough time to redirect other telescopes, and potentially even spacecraft, toward it before it passes through and disappears for good. The 3 interstellar visitors confirmed so far, Oumuamua, Borisov, and now 3I Atlas, are almost certainly not rare. Researchers increasingly believe objects like these have been quietly drifting past the sun since the solar system's earliest days. Humanity simply lacked the technology to notice them until the last decade. And now that the technology finally exists, the pace of discovery is genuinely expected to accelerate. If you have stuck with this story this far, here is something worth sitting with before we close it out. And it has nothing to do with fear and everything to do with scale. Right now, 3I Atlas is somewhere out past Jupiter's orbit, moving away from Earth at more than 60 kilometers a second, carrying chemistry that was locked into ice roughly 10 to 12 billion years ago, possibly before the star that originally hosted it had even finished dying. It will never slow down, never turn around, and never pass through our solar system again. Every instrument that was ever going to study it up close has already had its turn. What is left behind is not a mystery fully solved or a threat successfully avoided. It is a genuinely enormous data set sitting in the archives of Hubble, Webb, Swift, SPHEREx, TESS, Parker Solar Probe, Europa Clipper, and a dozen ground-based observatories, records of a piece of another part of the galaxy that happened to drift close enough for us to actually measure it once before it vanished for good. When the last telescope on Earth finally loses track of 3i Atlas for good, it will not really be an ending so much as a handoff. The comet keeps moving, carrying its 10 to 12 billion years of history back out into the dark it originally came from, while the data it left behind keeps getting studied, argued over, and refined for years after the object itself becomes unreachable by any instrument humanity currently has. Because its material formed so long ago and it has been drifting between stars for billions of years, researchers say it is essentially impossible to trace it back to its original parent star. That star may not even exist anymore. What we do know, with real confidence now, is that this will not be the last of its kind to visit us. And somewhere out there tonight, drifting silently through the space between stars, a fourth interstellar object is very likely already inbound. And right now, nobody on Earth has any idea it exists yet. If this kind of deep, fully sourced breakdown of the real science behind an object like this, not the exaggerated version, but the actual published research, is the kind of story you want more of, subscribing and turning on notifications means you will not miss it the moment the next interstellar visitor gets spotted. Drop a comment with which part of this surprised you the most, the age of the ice, the missing iron, or the water switching on far earlier than anyone expected, because it genuinely helps shape what gets covered in more depth next. And if you know someone who would find the idea of holding a piece of another star system in a telescope's crosshairs genuinely fascinating, share this with them, because moments like this one do not come around often, and this particular visitor is never coming back.